Hi, welcome back. Right, this is the next example, okay? Before I actually go over the question itself, I want to talk about why the curve looks like that, okay? It's really an interesting curve. So you've got two graphs drawn for you, and they're drawn in the textbook, okay? So you have y equals sine 2x, that's simple enough. You should know it looks like this between here and here, between 0 and pi over 2, that's easy. It's the next one, y equals sine x cos squared x. Okay, that's kind of an interesting one. Would you be able to do that if you weren't given it to you? I'm hoping the answer is yes. Yes, you would. Okay. If you look closely at it, it starts off at 0, of course, which is obvious because sine 0 is 0, so y is 0. It ends at pi over 2. Cosine pi over 2 is 0, and so all of that is 0 again. But that is obviously a maximum point, but then interestingly, the curve does this, isn't it? Okay, it's not one of those shapes, not your traditional sine or cosine shape, is it? Okay. It actually starts to, the gradient starts to decrease, it levels out, doesn't it? Okay, it gets flatter. Okay, and it looks like that's kind of going to be like a minimum point. That's really interesting, I think. Well, I find it interesting, and some of you should do as well. Okay. Yeah, so let's just have a look at that. How do we show that the graph does that? Well, before I actually get into some mathematics of it, sine x is positive between 0 and pi. Okay, so between here and say here, sine x is always positive. Cosine x is negative between pi over 2 and pi, but when you square it, that's going to be positive. So it's still going to be positive between pi over 2 and here. But because it is 0 at pi over 2, and because it's going to be positive between pi over 2 and pi, it's got to go up again. Because it comes down, it's got to go up again. It's going to be a minimum point, isn't it? Okay, let's just try and prove that, okay? And we're going to use differentiation to do that, of course. Calculus is always great when you want to prove results such as these, or show why the graph looks like that. This is one of the lovely things about calculus, you see. Maybe you want to pause the video, do that for me? Yeah, go on, give it a go, treat yourself. Go on. So you've got v du dx, so that's going to be cos x when you differentiate that, isn't it? And times by v, so cos cubed x, yeah? So v times du dx, cos cubed x. And then next, you have what? U dv dx. Okay, so let's write out u. We'll worry about the symbol in a minute. So u is sine x, and then derivative of cos squared x, that's going to be 2, let's put the 2 there, cos x times negative sine x. So cos x times by negative sine x, so it's going to be that. You okay with that? Let's just put it down by here. Yeah, so you've got cos squared x differential, you've got 2 cos x, and then times by negative sine x, which you can write as negative 2 sine x cos x. Right, and then when you times it by sine x, you get negative 2 sine squared x cos x. Yeah, good. Glad you're happy with that. Yeah. Then what we're doing when we're trying to find a stationary point, we'll set that equal to 0, aren't we? Okay, so we'll set that equal to 0. And what we'll do is we'll just factorise first of all, shall we? So cos x, so cos squared x, subtract 2 sine squared x, okay, is equal to 0, which leads us to one possibility, that is cos x equals 0, yeah, and from that you've got x is equal to pi over 2 or 3 pi over 2. Okay. Pi over 2 is that bit there. Okay. Stationary point when x equals pi over 2. Okay. Now you can prove it's a minimum point by doing what? Of course, you differentiate again. So if you differentiate, that again, which I'm not going to because it's going to take up a lot of board space, you should be able to then substitute that in, and you should prove that's going to be a minimum point. Okay. Why don't you do that? Okay. Treat yourself some more. Come on, come on. These days of isolation, you really need to treat yourself sometimes. Okay. So who could say no to calculus? Okay. So not this person. James Bond, he couldn't say no to calculus. You just don't see it on the screen. I bet behind the set, Daniel Craig is doing some serious calculus. Okay. Anyway, moving on. You've also got this possibility, haven't you? You've got cos squared x minus 2 sine squared x equals 0. So maybe just write that like this first of all. 2 sine squared x equals cos squared x. Yeah, do you agree with that? I'm so glad you said yes. And then let's just write it as tan squared x is equal to a half. This is great practice on solving trigonometric equations, of course. Okay, you can see why I like this question so much. It's like calculus, integration, differentiation, and trigonometric equations. and graph sketching. So I got all my favourite bits of maths into one single question. It's just great. This this is fantastic. Okay, it doesn't get too much better than this, to be honest. Okay, so you'd have tan x equals positive or negative. Do not forget the plus minus. Okay, positive, negative, 1 over 2, or 1 over root 2 if you want, and then x equals, and I'm sure you can figure that out. Okay. However, you should be able to have a rough guess that 1 over root 2, that's 0.707. Such a pity it's not 007 and it's 0.707. Ah! That would have been so annoying if that had been 007. But never mind. Yeah, 1 over root 2 is 0.707 something. You can check that on the calculator if you want. I am right. Okay. We do the inverse tan of that. Because it is less than 1, 0.707 is less than 1. Inverse tan of 1 is 45 degrees, pi over 4. Inverse tan of 1 over root 2, 0.707 is going to be less than pi over 4, which means it's going to be somewhere here. Hence the maximum point is between here and here, not quite the halfway point. Understand that? Rewind the video and play it again. Okay, if you want, and yeah, it makes sense. Get your calculator out, check if you want to think, oh, I didn't quite get it. Yeah, go on, do it again. Okay. And there are others, of course, but then don't forget we're only dealing with this domain here between 0 and pi over 2. Okay. Yeah, so that explains why the graph does that. So that's really interesting. I really like that curve. Okay. You might be looking at it and think, wow, yeah, what a view. To a kill. And I think it's a very appropriate point to leave it for that one, A View to a Kill. Watch A View to a Kill. Fantastic James Bond film. It's Roger Moore's last film. Okay, I went to the cinema to see that film. I remember going to the cinema. It was really good. Okay, really good. See you later, and stand by for the next one.